Hey everyone, I'd like to continue on and finish chapter 23 now with some variants on conjugate addition reactions. And let me get my weird face out of the way. Okay, and we covered conjugate additions back in chapter 19, and we said that there's a certain class of nucleophiles that prefers, given a choice, to add to the beta carbon of an alpha beta unsaturated carbonyl compound rather than directly to the carbonyl. Others add directly to the carbonyl. And so please do review that back in chapter 19 if you need to brush up on that. We said even at the time that enolates were an example of a nucleophile that prefers to add in a conjugate fashion, even though at the time we didn't exactly know what an enolate was, except maybe by analogy. But I wanted to refresh your memory on conjugate additions and also give you an example of such a reaction. And it's only an example. I just picked a couple of compounds out of my head. But I think it illustrates some good ideas to bear in mind as we analyze these mechanisms and as we learn them. So let us say that we took our old friend methyl acetoacetate, and we treated it first with sodium methoxide and methanol, and then waited for everything to finish reacting, and then added dilute acid as just a workup step, again, carefully, so as not to hydrolyze any esters or any such thing. Well, of course, we would expect the methoxide ion. Again, notice, of course, we're matching the ester, the base, and the alcohol all up so that we don't get any kind of scrambling. So the methoxide ion will pull off either of these two particularly acidic protons, and we'll get the enolate, which this is just one of the acceptable resonance forms. If you wanted to draw the minus charge in carbon, fine. If you wanted to show the minus charge in the ester, oxygen, also fine. Just three different ways of drawing the same thing. However you choose to draw this enolate, that then will react in a Michael or conjugate fashion. So if we treated it, for example, with cyclopentenone, this compound here, it would add to the beta carbon, right? Alpha, beta. So it'll add to the beta carbon and you'll get actually another enolate. I expect this enolate, since it isn't particularly stabilized, will relatively quickly pull a proton off of methanol and give our product. So we're done, right? Well, not so fast. We need always to be thinking about this. We're still in an alkaline medium. Are there any particularly acidic protons that can get pulled off, which, just like we had also recently, which we cannot prevent from being pulled off, and so we need to show that in our mechanism. And there is one more acidic proton here. In this case, I might have picked an example that didn't have, maybe there was a methyl group there instead. And in that case, we'd be done. But since there is still an acidic proton, that's going to get pulled off by our methoxide, and we can't stop it from happening. So it's this enolate that's actually going to be floating around quite happily in our methanolic solution until we work the reaction up by adding dilute aqueous acid. And we add that real carefully, nice and slow, keeping it cold. The first thing that the acid will do is neutralize any leftover methoxide ion and convert it to methanol. And after that, it will start protonating the, and presto changeo, we're back. That's much more better. So we put the proton back in our enolate intermediate and we get our neutral product. So this is an example of a conjugate addition of an enolate. Enolates are a nucleophile that prefer to add in this fashion, just like we covered back in chapter 19. So please do go back and review that if you need to. A variant in all of this is the Stork Enamine reaction. And we talked about enamines also back in chapter 19, named after Nobel Prize-winning organic chemist Gilbert Stork. And the thing to be aware of is that enamines are very much like enolates, both in terms of structure and in terms of reactivity. And if you imagine instead of this nitrogen over here that were O-, it's very much the same type of animal, right? You've still got an electron-rich atom here with a lone pair that it can donate. And so here I've taken the pyrrolidine enamine of cyclohexanone. That might not be a bad thing for you to review, but you can, if you want to see how this compound is made, you take pyrrolidine, which is a 5-membered cyclic amine with 4 CH2s and NH, and then you add that and an acid catalyst to cyclohexanone, and you will eventually, after loss of water, get this enamine. Probably wouldn't be a bad idea for you to review that, especially since one of these days eventually, God willing, and the creek don't rise and we all survive this, there's going to be a final exam. So doesn't do any harm to review that. So like I said, pyrrolidine, cyclohexanone, acid catalyst. Ready, go. Okay, so now we have our enamine, and this will add to an alpha beta unsaturated aldehyde or ketone in exactly the same way. We don't even need to make an anion. It just adds. And so we get an intermediate that looks like this. Here's one of those rare cases where we have both a plus charge and a minus charge. And I think we're on solid ground doing this because these reactions generally are around and about pH 7. As I look at what I'm given here, just the alcohol solvent, I don't see anything either strongly acidic or strongly basic. And so being relatively near pH 7, I think we're okay. I think we're on solid ground writing it like this. So we could imagine reprotonating this enolate with a molecule of ethanol, our solvent, and you would get this species. We can then hydrolyze off the iminium group and get back our ketone. And that was the nature of the Stork Enamine reaction. So like I said, any mechanism problem I give you, I do tend to show you the the product to aim for, as well as the starting material that you're beginning with. If you need to review this mechanism of iminium hydrolysis, I did give it to you in the class notes on the next page. However, I'm not going to go over that just now because we've already covered that. That was in chapter 19. And all you need to do is go from the ketone back to this iminium species. We talked about the reaction going in this direction. And so you just rewind that. You do that entire mechanism in reverse. And that's the correct mechanism for that hydrolysis. And so in the end, you will get a molecule of pyrrolidine, as you see over here. That's going to go into our waste jug. Our major organic product will be this diketone here in that particular case. One last variant on this. This is again one of those name reactions. And really in either of these cases, Stork enamine or Robinson annulation, I'm as always, and I think you know me by now, I'm less concerned that you know what they're called than that you understand how these reactions work and are able to work out similar mechanisms on examples that maybe are not identical to this. So I gave an example of a problem that involves a Robinson annulation, which is just another Michael addition, in your textbook here. So in the setup of this reaction, we're going to take this compound, which by the way looks an awful lot like this one. You've again got an acidic proton that's between two carbonyls. And so sodium ethoxide is more than a strong enough base to pull that off. You could probably have even gotten away with something slightly weaker. And actually, we didn't even need to be careful with the choice of bases. This isn't an ester, so you don't even need to worry about scrambling esters. Anyway, when you deprotonate this dione with our base, you get this enolate, which there's at least 2 other resonance forms. Whichever way you choose to draw that enolate, that will now add into our methylvinyl ketone at the beta carbon, so in a conjugate fashion. The next structure is an enolate. So we will simply protonate that enolate using our solvent, using whatever the solvent is that we're given. In this case, it's ethanol. But now we have the possibility to form the enolate on the other side. And the reason that's important, as opposed to this enolate over here, is this enolate could not do an intramolecular aldol reaction. You can try it. You'd see it'd be a 4-membered ring. 1, 2, 3, 4. So that's no good. But you can get this other enolate. Now, true enough, that would only happen little by little in very low concentrations. However, once you form this other enolate, there's a very rapid pathway with a 6-membered transition state to form a 6-membered ring, as you see over here. And this blue bond over here, with apologies to those of you who are colorblind, which I'm constantly aware of. It's not as rare as you might think. But in any case, this bond here is the new bond that we form. And I just used, again, an arbitrary numbering system just to keep my carbon straight. You can certainly do that too, if you find that helpful. So now we can protonate our alkoxide ion using our solvent. But again, we're in a situation where there's still some acidic protons left. And as such, we cannot stop the ethoxide from pulling off either one of these protons or one of those protons. And it doesn't really matter which you consider. But there's an extra possibility with these two that you don't find with those two. Remember the E1CB elimination that we discussed earlier. This is an initial aldol adduct, just like the ones we had at the beginning of the chapter. We can't get that if we deprotonate in the other side. But if we deprotonate here, we get this enolate, which can now kick out hydroxide ion in an E1CB mechanism and get this nice, stable, tri-substituted double bond that is also conjugated to the carbonyl. So that type of thing is another thing that you need to watch out for as being possible. And again, if you're given the structure of the product to aim for, as you generally will be, it's much easier to look out for that sort of thing. But this is, again, if I had to give you my best advice, these sorts of ideas, do I pull off another proton? What happens? Is there an E1CB? I don't recommend trying to memorize that beforehand. If you memorize something beforehand, then you can memorize beforehand these sorts of things can happen, and you can practice so that you get an idea of what to look for when they will happen. But don't go into autopilot. This is the sort of thing that you will apply situationally, depending on what you're given. There is, again, a chapter on biological carbonyl condensation reactions. We would have gone over a few examples of that in chapter 29, which unfortunately, due to the shortened semester, we need to skip. I'm actually thinking of putting up my lectures that I would have given on chapter 29 anyway, or lectures, but you will not be responsible ever for anything in chapter 29. But I sense that probably some of you at least are interested in that. So I will seriously consider doing that as we get near the end of the term. As long as I have enough time to do so, I will do that. But other than that, that's basically it for chapter 23. We will go on next time and finally finish the spectroscopy chapter, when we'll cover proton NMR spectroscopy, where I think you will find that you had reason to trust me when I said, let's put off proton NMR for later. It's a good deal more complicated than carbon NMR, but we'll tackle it. We can handle it now. So that's about it for now. Everyone have a good day, and we'll see you next time.